Ok, buenos días. Me llamo Daniel Phillips. Mi español es muy malo, así que continuaré en inglés ahora. ¿Está bien? Ok, gracias. Okay, good. Yeah, thanks again. So my name is Daniel Phillips. I'm from Chicago. Today I'm going to be talking about WebAssembly and Python. Who's heard of WebAssembly? Bien. Who has used WebAssembly? Nada. Oh, uno. Okay, gracias. Okay, good. All right, excellent. Okay, good. All right, so we'll get to it. A little bit about me first. Like I said, my name's Daniel. I'm an engineer at a small startup called Loophole Labs, where I mostly focus on server-side WebAssembly. But Loophole Labs does many different things. We do some stuff with mostly software infrastructure. One of our main products is doing live migration of running VMs. So you can take a VM and you can run it in Chicago, in Copenhagen, in Tokyo, and you can move it across all these continents with less than 100 milliseconds of downtime. It's pretty cool. Check it out. This talk won't be about that, but if you want to chat more about that, I'd be happy to discuss more after. I work on a project called the Scale Function Runtime, which is a WebAssembly-based plugin framework that uses WebAssembly on the server, and it allows you to write code in many different languages, including Python, and run that code with other code in the same process, which I'm going to talk more about those details a little bit later. On the internet, I am D_Philla, so on Twitter, on X, on GitHub, it's a dash, not an underscore, because they don't allow underscores. So dphilla if you're interested. And then also, I live in Chicago, and I run the Wasm Chicago group. It's like a research meetup group that's dedicated to emerging technologies around WebAssembly. Okay, so what is WebAssembly? We're going to sort of talk in broad strokes here and then become a little bit more specific as we move through this presentation, especially at the beginning. So this is directly from the specification. WebAssembly is a safe, portable, low-level code format designed for efficient execution and compact representation. It's a safe sandboxed execution environment. It has a deny by default assumption when it comes to security, and it makes no assumptions about languages or hosts. This is very important. The best way to think about it is as a virtual CPU, right? So what does this mean? It's another type of compilation target. You compile things to native platforms like x86 or ARM64, whatever, and WebAssembly is another target like that. So you can compile things to WebAssembly. It's a virtualized ISA, an instruction set architecture. It uses a bytecode binary format, but that's more of just the detail of the implementation. And it uses an abstract stack machine, which I'm not going to talk about too much today. Those are more of the low-level details. So what does this actually mean? In a broad sense, it's just another architecture. It's another platform to run native code, except this native code is virtualized. So the biggest difference is that it's virtualized. It needs a runtime to translate the WebAssembly code into machine code on whatever native platform that you're on. And it's universal, right? So everyone here who has a browser that is either Edge, Firefox, Chrome, whatever, has a WebAssembly 1.0 runtime in it. Browsers can run two things, JavaScript and WebAssembly, with two different engines, right? So, is it a client-side technology? This is where it gets a little bit interesting and maybe a little bit different from what many of you have heard. Remember, from the spec, we said it's a safe sandbox execution environment. It makes no assumption about languages or hosts. It makes no assumption about what languages you can compile to WebAssembly, and it makes no assumption about where that WebAssembly will run. So if you look in the specification, it says nothing about the browser. You can also think of WebAssembly in an interesting way because the startup times for WebAssembly are extremely fast, and this was by design. So you can start relatively large chunks of code in nano to microseconds. And it's a universal compilation target. There's a joke in the WebAssembly community that Wasm WebAssembly, Wasm is short for WebAssembly, is neither web nor is it assembly. It has nothing to do with the web, and it really has not a lot to do with assembly. So, server-side WebAssembly. This is what I like to call cloud infrastructure's penicillin moment. Penicillin, right, the drug that people take for bacterial infections, this was discovered by mistake, right? WebAssembly and its usefulness on the server maybe was also sort of discovered in this same way. We can think of abstractions when it comes to running code, untrusted code on trusted devices. We started with bare metal, and then we moved to VMs, and then we moved to containers, and then now, if you squint, we can kind of think of the next wave as being WebAssembly. I'm going to talk about this more, right? I said the subtitle of this talk was Smaller, Faster, Safer, and Much More Universal. And do we have people in here who have used Docker containers? Probably everyone. Yes, of course. Good. So, not sure if you can read this, but this was the founder of Docker talking about Wasm. He said, if Wasm and WASI, I'll talk about WASI in a minute, if they had existed in 2008, we wouldn't have needed to create Docker. That's how important it is. WebAssembly on the server is the future of computing. A standardized system interface was the missing link. Let's hope WASI is up to the task. So WASI I'll discuss in 1 minute. But I'm going to sort of talk through why the founder of Docker thinks this about WebAssembly. So, WASI. We have WebAssembly, which is a secure, tiny sandbox that can execute any code, theoretically, if it compiles to WebAssembly, right? But that doesn't do much for us if we can't do things like make a network connection or talk to a file system, things like this. So we need some kind of interface to those systems, right? And this is where WASI comes in. It's the WebAssembly System Interface. Sometimes people are calling it the WebAssembly Standard Interface. It started in 2009. It's kind of like POSIX, right? POSIX defines a set of interfaces, which is sort of the basis for all Unix systems. Python itself, if anyone in here has had the fun time of compiling Python from source, you will know that Python makes a lot of assumptions about Unix itself. It typically runs, CPython in particular, runs in a Unix environment. Capability-based security. Has anyone heard of Plan 9, the operating system? Plan 9? No? No one my age or older? Nobody? Okay. Yeah, all right. Yes. Okay, cool. Uno. Bien. So Plan 9 is an operating system that came right after Unix by the same people at Bell Labs. And the purpose of Plan 9 was to fix the problems with Unix. And of course, Plan 9 never really took off like Unix did. They had a lot of things with Unix that they realized after the fact, like if you've ever done low-level system call work, everything is a file, right? Everything is a file. Well, maybe a socket isn't really a file. I don't know. It depends who you talk to. We can talk more about that. Okay, so WASI. WASI has a few different standards. It's evolving right now. There's preview 1, 2, and 3. Right now it's on preview 2. Do you need to use WASI? No, you don't. WASI is not supported in the browsers. WASI is for running WebAssembly on the server, right? Cool. Okay, so I'm going to briefly talk about the scale plugin framework that I use. So thinking about what I just told you about WebAssembly, we can think about, right, if we squint, it kind of looks like a container, but it's smaller, and you can use any language, and it compiles down to run at near native speed. So that's actually kind of perfect for something like a plugin framework, where you can take code written in any language and run it in any language, right? So the scale framework, this is what I work on at my day job. This is a plugin framework where you can, right now you can use Rust, Python, Go, TypeScript, and you can run code from Rust, Go, Python, TypeScript in any of those other languages, right? And you can do this without having to worry about translating the types and how this works because of a few things that we've developed. It also works as a serverless function runtime, right? Serverless functions are a really good fit for WebAssembly. I'll talk about that a little bit more. And you can do polyglot programming in the same runtime environment, okay? Has anyone tried to use Python in another language? Okay, a couple people, a couple brave souls, yeah. Has anyone tried to use another language in Python? Yeah, okay, cool. Yeah, so I was a Ruby developer for years, years ago, before I got into infrastructure, and I remember trying to do machine learning stuff from Ruby in Python, and it was a disaster. It was a huge disaster. The cool thing about WebAssembly is that if you can compile all of this to WebAssembly and you can figure out the types and you can figure out the type translation, which we've done with Scale, you can run Python, Ruby, Go, Java, literally all four of those in the same Unix process at the same time. And this is sort of one of the things about when you have this universal ISA, if everything can compile to that, and you can figure out the types, which is tough, then you can have true polyglot programming, right? So Scale is written in Golang. We use Golang because it's a quick and easier systems language. We do a lot of Rust, but Golang is a little bit quicker to iterate with. So the interesting thing about Scale, too, I'll say, is why do we need something like this? Well, we did some experiments where we noticed, like, for example, in Golang, the regex library is kind of slow, okay? So what we did was, using the Scale framework, we took Rust's regex library, compiled it with Scale to WebAssembly, ran that inside Golang, and we saw that doing that in WebAssembly with Scale in Golang, the regex library was 4 times faster than native code, 4 times faster than Go's native code, right? So the cool thing about this is you only need to have one SDK or one library, right? If you're a vendor like Amazon or Google or whatever, and you have a library that wraps some service that you have to write it in Java, Elixir, Erlang, whatever, like in all these different languages. But what if you only had to write it once, and you could import a WebAssembly module and then run it there, right? It kind of obviates the need for multiple different language libraries when they can all have one common interface. Cool. So yeah, some people that have built Python from source. Yeah, it's kind of tough, right? If you do it, especially if you do it on some sort of esoteric architecture. So when you build Python from source, specifically C Python, there are a lot of assumptions that you need to build the runtime, okay? Unix is the first one. You need to have a file system. You need to have dynamic linking. You need to be able to understand that things will be there on the system when you plan to build it, right? You need syscalls and some kind of libc that are typically POSIX-based, right? So we had to do all of this in WebAssembly, and remember, WebAssembly is just an architecture. It's like just assembly, basically, right? So it's as if we have none of those things. We don't have a file system, we don't have Unix, we don't have any of these things. So we have to figure out how we can sort of stub those things out and replace certain items to make Python think that it's being built on a Unix system when it's actually being built on a new architecture, which is WebAssembly. So there's a limited number of support for syscalls. That was a pain point. That was a tough one. There's no pthread API. This is very technical. I'm not going to get into it here, but this was something that we had to work around. No socket APIs. We also had to figure this out. And no comprehensive signal support if you've ever used Linux signals. If you want deep detail on how we did this, like not me, actually, Christian Himes did most of this. You can watch his Wasm Day talk from 2022. I'll post this on Twitter and stuff. It's a really great talk, but he talks about the internals of building Python to WebAssembly specifically. Cool. So now I'm going to talk about a project that I work on that's a personal project, but I've been working on it off and on for a couple of years. And my goal with this is to sort of make this whole process easier so that someone who wants to run Python and WebAssembly doesn't have to think about all of this internal stuff, and you can just compile something just like you do with a container, but maybe make it easier and run it in more places, safer and faster. Cool, so this is Boxer. And this goes to boxer.dev. Trust me, it's not malware. So what Boxer does is it takes a container declaration and it turns it into a Wasm binary, right? So you can take a Docker file and then it turns it into a Wasm binary with a runtime, and then all of those interfaces and all of that hard work that I was talking about, it's just kind of done magically for you, right? And I'm going to show you a little demo of this. Well, first I'm going to talk about what's in it. So, what's in a Wasm box, or a box, right? Boxer, it's kind of like a play on words, right? Like boxing, but then also a box, like it's turning things into a box. You've got a base layer, much like you would see in a container image, which sort of sets up the interfaces for what the code needs to run. You've got a virtualized file system and virtualized system code, which means like those things that aren't available in WebAssembly, depending on the environment that you're in, we're going to make the code think that it's there. Right? A compiled runtime, meaning like the version of Python that you're running, we're going to bring that C Python that we compiled to WebAssembly for you into that box. And then the user source code, right? And this all gets nicely wrapped up in a tiny little box. See? Yeah? Okay. Gracias. All right. And then exports and imports, which I'll also talk about. So, kind of what I just mentioned. This is an example Docker file. You got from Ubuntu latest, which means that this is going to set up what the code thinks is an Ubuntu system, because all it needs to know is the interfaces, right? Ubuntu, when you run a Docker container, kind of fakes out whether or not the underlying system has Ubuntu. It uses POSIX to make it think that it's there, so it's kind of the same thing. We have a virtualized file system. You can copy from your local environment to the container itself, to the box itself, set up the working directory, and then the command, right? This also uses a project of mine called the Wasm VFS, which is a virtualized POSIX file system implemented for WebAssembly. This is written in Rust. I'm not going to talk about the specifics of this because I'd like to get to the demo, but if you're interested, you can check it out on my GitHub. It's dphila, dphila, Wasm VFS, and there's a lot more detail here. So, demo. Okay, cool. So, Boxer. This is Boxer. And let's see. I'm going to talk about this. This is you can tell I'm an excellent front-end developer, right? So, I'm going to walk through a little demo of what I just described with Boxer, right? So this is using a Docker file to create a WebAssembly distribution. That's the long and short of it, right? This just goes back to the main page. And so, we go here, all right? So this is the repo. Right now it's not set up with like release patterns and stuff. This is, if you want to use it, you have to pull it down and compile it yourself. I'm sorry. Soon, it will be set up to be released and used like a real tool. But if you check this out, so this is the tool that we're going to be using, okay? And if we go here, you can see this is a Docker file. And in fact, this comes from the official Docker image on the Docker Hub, on the Docker registry, right, for using Python 3, okay? So have we seen, people have seen something like this before, right? We've all kind of seen this before, yeah. So, so using Python 3, we're going to get the sort of runtime layer here. We're going to set up the working directory. We're going to copy the source code into the code of the WebAssembly binary. And then we're going to run my script, right? Okay? So, this is my script. Ignore this. And this. There we go. So this is my script. What this does, this is just a very simple, thanks. This is just a very simple math that like is going to do some square rooting, and it's going to make like, you know, it's going to do some very simple operations and print them, and that's the long and short of it. You can see we're not using any extra dependencies, no other native dependencies, but just to kind of get this working, right? So this is Box. Box is the CLI tool. Ignore my Rust warnings that I promise I will fix before I release this. But yeah, so this is Boxer 0.1, and what we're going to do is, can we read this? Not really, huh? Let me do this. Okay, so we're going to do a box build, and then we're going to pass in the Docker file, that Docker file that I just showed you, right? So Python base image is located, which means the Python 3 runtime. It's bundling up the runtime, the file system. Sometimes that can be relatively big, but compared to a container, it's pretty tiny, which I'm going to talk about in a second. So it bundled the runtime, the source code, and the file system, and now that's all in one single WebAssembly binary. And then do box run. Yeah, and that is Python running on my machine in WebAssembly. And the user has no idea that it's different, right? So that's kind of fun. And we can actually do the same thing, right? Because WebAssembly not only runs on my machine, but the exact same code can run in my browser, right? So this is a demo that I was working on getting finished before this talk, and I didn't finish it, so it's a work in progress. But what I would like to show you is we do something like this. Let me just see if I can remember what the repo is. Yeah. Okay, cool. So I made this little repo here. This is on GitHub. It's open. It's public. Same code, right? Basically, except I left a print statement in there. Can you see that? Yeah. All right, so Python boxer example. We're going to go back here. GitHub.com, dphillip, Python boxer example. And what this is going to do, so I made a little script that pulls that in from GitHub. You can see it links it right here. This is the same Docker file that I had locally, right? And we have a build tool that is also written in WebAssembly that I can run anywhere also. So that means I can build this Docker container in my browser, and I can run it here, and I can run it locally, right? So if we think about that for a second, that means I can run the same stuff I would run in a container, literally in my browser, and also locally on my machine, right? With slight differences. And like I said, this doesn't work yet, but it definitely will. So I've got this shirt also. I'm going to wear this shirt around. Stop me, and I'll give you one if you want. I got a few of them. But it's also, I'd like to get this working either tonight or tomorrow morning. So I didn't quite make it happen. I had a little trouble when I first got here, and so this is pending. So yeah, check it out. So the idea there is we can do some interesting things, right? Like if people remember the beginning of Node.js, there was this big, exciting term, isomorphic JavaScript, right? Anyone know that term? So like isomorphic JavaScript was like, oh, you could run it in the browser, you could run it on the server, it's the same code. It turned out it wasn't really the same code, but it came close. This, though, is exactly the same code in exactly the same runtime environment across multiple hosts, including browsers, including servers, including embedded devices, all these things. So I'm going to try to run through the rest of this because I am running out of time and I'd like to get to some questions. So some caveats. Threads. WebAssembly is single-threaded, but what you can do is a lot of tricks to make the underlying runtime think that there are threads, okay? I'm talking about green threads here. So you can do things like fast stack switching. Async is coming, and threads are coming to WebAssembly, but if you think about it in a virtualized ISA on any different type of architecture, setting up true multi-threading and async and threads is very difficult. So that will probably be the last big piece added to WebAssembly. Native dependencies. For people who have done a lot of machine learning and like math-heavy stuff, data science in Python, there's some pretty esoteric languages that Python wraps, right? We have things like, I think like Fortran, we definitely have C, right? There's like C++, tons of stuff. So we can deal with this in WebAssembly, but we have to sort of figure out how to compile each of those things separately and then figure out the interfaces. This is a thing that I had ChatGPT make for me, and it kind of illustrates my point. You've got a container, you've got a box. It's the same app. And just to kind of look at that, Python container images can be huge, right? I've worked on infrastructure teams that have worked with app teams that had containers that were not just 80 to 900 megabytes, but maybe like gigabytes, maybe like tens of gigabytes, right? that would take 30 seconds or 2 minutes to start up, right? Startup speed for these size of containers. By the way, this is the same code that I just showed you. That is the, if you cut out the standard lib, maybe you get down to 80, but maybe it's still more like, it could be still up to 100 with a basic Python build, right? Startup speed, 800 milliseconds to 2 seconds. Security model, I'm not gonna get into this, but with kernels, with containers, you use a shared kernel, right? So containers give you the illusion of a sandbox, but what they're actually using is the underlying host's kernel together. So that is a security vector that is completely different in WebAssembly because you're actually just using isolated machine code at the lowest level. The same code in a box, in Boxer, maybe 16 megabytes. That's even with the standard lib. The startup speed is 100 microseconds, even in the browser. Maybe 1 millisecond in the browser, right? This is a virtualized environment. Security models, virtualized sandbox, machine code execution. So what does this mean for the future? This means in the future we'll have full support for libc syscall interfaces, runtime host function generation, right? This means that Python code that I deployed that can deploy to the browser, Boxer, we have a couple people working on this too, some friends of mine, is that what if you could have networking in the browser just like you do on a server, right? So there's some interesting experiments that we're doing with TCP over WebSockets and WebRTC that sort of brings the same semantics, which means that you can run things like you could run C code in the browser with a socket implementation, and you could take stuff like Fast API and compile that, run it in the browser, and there would only be slight latency differences. In fact, maybe even less depending on the WebRTC implementation. And that means we have to modulize the kernel, right? So what we're doing is we're taking pieces of the Linux kernel and we are working on bringing them to WebAssembly and making it sort of this like new de facto compilation target, right? Sounds crazy, but if you want to talk more about this, hit me up and I could talk all night about it. Yeah, a paradigm shift. So then what we have is, if we have this polyglot environment where we're running all of this different type of code with machine execution at the sub-process level, maybe we don't even need a kernel. Maybe we can just use composable, universal, Wasm-based operating systems in a distributed fashion. I'm not going to try to get too lofty here, but that's kind of the bright future, right? And there's some things to watch out for if you're interested in this space. You should take a look at WASI, the WebAssembly System Interface, and WALI, which is the WebAssembly Linux interface. We've been doing some work with them to sort of work on this virtualization layer, and there's some really cool ideas. A lot of this stuff is sort of research-based. WALI comes out of a group at Carnegie Mellon University in Pittsburgh in the United States, and it's all very sort of under rapid development, but it is on its way. And then finally, I didn't talk about this at all, but there's a huge push for using WebAssembly in embedded devices, okay? So embedded devices, if you've ever had to reflash a bare metal device, it's a huge pain, right? With WebAssembly, you could run code that isn't some sort of esoteric, needing some sort of esoteric C compiler, but you could just use WebAssembly and it can run at near native speeds, and you can just do updates as long as you've got a WebAssembly runtime on that device. So some people at Sony, some people at BMW and Porsche, some people at Siemens are doing a lot of really interesting work using WebAssembly in IoT devices, in microcontrollers, and in embedded devices. So if you want to talk more about that, I'd also love to chat about it. Yeah, so what does this give us then? It gives us true isomorphism, right? You can literally run the same code anywhere you want, in the browser, on an embedded device, on your machine. It runs basically as fast in most cases, and it will continue to get faster as native code in many respects. And you can fully appreciate that code execution is safely sandboxed, and it sort of gives us this new universality and true isomorphism that people have been sort of seeking for a while. Cool, thank you very much.